In this, our final lecture, I hope to fulfill a promise I made earlier in the course, while also making a final link to the Prolog programming language. As you may recall, the Sequent calculus includes a lot of rules, and you may feel there is a lot of memorization that you might have to do. But as it turns out, the number of truly primitive inferences in the Sequent calculus is very small. The problem, as we've seen several times already, is that ordinary logic has lots of connectives because people like to use all these things to express mathematical properties. But they are many more than necessary. We have seen a number of different ways of compiling down logical formulas into different normal forms, conjunctive or disjunctive, or clause form, well, which is conjunctive normal form, or BDDs. They are all ways of compiling formulas down to a smaller or canonical format. What we're going to do now is the same idea again. So you see, as it says here, if you have 7 logical symbols for first order logic with left and right sequent calculus rules, that's already 14 rules, 4 more in modal logic, plus you have other things like the basic sequent and the cut rule. But we can simplify this massively. The idea is to work with negation normal form. That gets rid of implies and if and only if at a stroke. But it does more. Since negation will now only be applied to atomic symbols, we don't need the negation rules either. So we have reduced the number of connectives in the case of first order logic from 7 down to 4. But now a really massive simplification becomes available. If you recall your sequent calculus rules, and no doubt all of you have already committed them to memory, you will recall that certain rules, such as the rules for implies and for negation, move formulas from one side of the sequent arrow to the other. That is because they involve negation either explicitly or implicitly. But if you look at the sequent calculus rules for these logical connectives here, or indeed also the modal box and diamond, none of those rules move a formula from one side of the sequent arrow to the other. That means if you begin with a sequent that has formulas only on one side, then the rest of your proof will consist entirely of sequents of the same form, that is, with formulas always on the same side. That allows us to throw away a further half of the remaining rules. So here is the Tableau calculus that we get. Now incidentally, okay, here we have only the left side of each sequent arrow. If you look carefully, you may note that many of these are the sequent calculus rules you already know. So here we have and on the left. It's the same rule as before. Now, the deltas, remember that we had a delta here and a delta there to the right of the arrow in the sequent calculus version. But that is just a placeholder for however many formulas we may have there. If in fact there are no formulas there, it doesn't make any difference. So here, by leaving off the deltas, we are simply emphasizing that there will never be any formulas on the right-hand side. Nevertheless, it is the same rule. Likewise, or on the left is exactly the same as the Sequent calculus version. The same for all on the left exists on the left. All of them exactly the same as the Sequent calculus version. What's different? Well, basic sequents look different. Now you remember a basic sequent would have a certain formula A on the left and on the right of the sequent arrow. Well, now we don't have anything to the right of the sequent arrow, so we have to write our basic sequent like this with a formula appearing in both positive and negative occurrences. And incidentally, though we have written not A, and you know in the Sequent calculus version, a basic sequent could involve a large and complex formula. We will not see that anymore because with negation normal form, negation can only be applied to an atomic symbol, to a predicate symbol. And I suppose potentially it means proofs could be longer in the Tableau calculus, because if we reach a basic sequent in the Sequent calculus with some non-trivial formula, here that would not be available to us, and we would need to continue breaking down that formula until we got a lot of basic sequence for all its atomic constituents. I don't want to say a huge amount about the cut rule because we've never used it really. But if you look at the original cut rule of the Sequent calculus, you will recall that there, this formula A was on the right-hand side. We don't have a right-hand side anymore, so we have it negated on the left-hand side. Actually, rather more significant is the point that, as I just said, the formula A, the so-called cut formula, can only be atomic, which is a hint to me at least that in this particular calculus the cut rule is completely useless. The whole point of cut in the Sequent calculus is that you could prove a large and complex formula once and use it repeatedly. And I am not sure if there is a big benefit from proving an atomic symbol once and then using it repeatedly. But of course, I could be wrong here. What is this little thing at the bottom of the slide? Well, it is the same condition on the X exists on the left rule as we know already from the Sequent calculus. So there's nothing to discuss or motivate here. We move on to modal logic, and the situation is the same. We have box on the left, diamond on the left. We have this weird thing of erasing all the assumptions that do not begin with a box, and all of that is exactly the same as in the Sequent calculus rules. All we have done is throw away the right-hand sides. Now, it's worth noting, what does it even mean to have an empty left-hand side? And here you must remember, the left-hand side is interpreted as a disjunction. The empty disjunction is false. So we are working entirely with bundles of formulas that imply false, or if you like, bundles of formulas that cannot all be true. So when we use this Tableau calculus, we are doing proof by contradiction, something that we should be used to from all the clause method work that we have been doing. Now let's suppose you don't like proof by contradiction, or if you think that the choice of the left side was somehow arbitrary or even biased. Well, so what if the right side demand to have their day in the sun? What would happen then if we, instead of throwing away the left, we threw away, instead of throwing away the right, what if we threw away the left instead and made a right side only version? It turns out that although superficially it would look very different, there would be no difference whatever in the proofs. By duality, if you took your formula and made two separate proofs, one where you put it on the left-hand side, which typically involves the negation step, or put it on the right-hand side after converting to negation normal form and so on, and then did a proof in each of the respective calculi, you would get identical proofs. That is, there would be a duality, so instead of and on the right, you would have or on the left, and so on for all the connectors, and the two proofs would be mirror images of one another. So from the point of view of performance, let's say, or lengths of proofs, or anything like that, you would find there is no difference whatever between the left side and the right side system. Nobody ever looks at the right side system. I guess they find proof by contradiction quite natural in this world. So here's an example. We want to prove this formula up here. So here we're going to kind of be a little bit like a resolution in that we're going to negate it first. Now the reason we're negating is because we need to put it onto the left side. So to prove a formula A, as we remember, is the same as refuting the formula not A. So we are going to negate this thing, convert it to negation normal form, and then put it on the left-hand side of the sequent arrow. A proof of this sequent will be a refutation of the negation of the original formula. Okay, now why, by the way, have we already turned it into three separate formulas there? Well, strictly speaking, it should have been one formula, but I'm just saving a bit of trivial steps. So we should have been using and on the left explicitly. I don't want to go through all the work of converting this to negation normal form, but as I've hinted many times, if you are negating a formula that has implies in it, what you do is you keep these things positive and that thing becomes negative. Now, I seem to have scrambled all these things up for some reason, but this P here has ended up as that P in the sequent. The for all y qy in the original conjecture, this was the only thing that eventually gets negated, so it turns into exists y, not qy. Finally, this for all x, p implies qx, is kept. All we do is, because we're converting to negation normal form, you'll see that the implication arrow goes to not p or q. And so I have kind of, I guess I did this in a mood of converting into clauses, which may be another reason why I did all the and on the left inferences implicitly. But that's all right. You can get away with this. So this sequent at the bottom of the page, at the bottom of the slide, is what we begin with. And now it's just a sequent proof. So, as usual, we have the choice between the exists and the for all, those being the outermost connectives. We don't know what to do with for all because we have no reasonable candidate for a term to replace x by. So we deal with the exists instead. We can do that because remember the condition y must not appear free in the conclusion, and indeed it does not. This y, of course, being a bound occurrence. So we can strip away the existential quantifier and we get the next line here. So we now know p is true and not q of y holds. Now we have to, well, we only have one connective left that we can do anything with. That's the universal quantifier. we finally have a plausible term to substitute for it, namely y. So we do that. Now we have not p or q of y. And the final step here will be to do or on the left, which is the only thing we can do here, really. Now we have two basic sequents. As I said, okay, and it's not exactly a sequent calculus proof, because when we get to the basic sequence, we have p and not p both on the left side. Or we also have not qy and qy both on the left side. So that proof is finished. Now let's switch to something slightly different. And this is where it gets interesting, and this is where we are starting to make a transition, I could say, from the sequent calculus to something resembling resolution. So what if we want to bring unification into the Tableau calculus? To do that, we need to reformulate our calculus a bit. We get a thing that's called the free variable Tableau calculus. What we do now is we say, when we do for all on the left, instead of your having to think up a particular term, as has always been the case until now, you're now going to plug in a new variable, let's say z in this instance, and then when you do a basic sequent, you allow z to be changed by unification. So if I have some sequent of the form not a and b, remember a will in practice have to be an atomic formula because we're in negation normal form, we now will allow unification to make a and b the same. Now you might imagine this is cheating, especially after what I just said about the need to do existential quantifiers before universal quantifiers. Now you might say, can I get rid of the universal quantifier first, then put in this new variable, then eliminate the existential variable, and then say that this variable is the same as the existential variable? And isn't that going to kind of, in a backhanded way, or whatever, through the back door is the metaphor I'm reaching for, somehow violate the condition of the existential rule? Well, don't you worry, we are going to get rid of the existential rule altogether through Skolemization. Oh, and the thing I overlooked for a moment, when we do this unification, as always, unification has side effects. So although you are replacing z by 3, say, the point is that you don't just do it in that one place, but everywhere in your proof where that variable occurs, all of them have to be updated in the same way. That is necessary if this is going to make any sense. Okay, what role is Skolemization going to play here? Well, we've seen Skolemization already. It is the same concept. I don't need to remind you how it works. Well, I will anyway. Let's look at this formula here. For all y exists z. So here we have an existential quantifier within the scope of a universal quantifier. So this z will need to be replaced by a new function symbol depending on y, and in general depending on all the universally quantified variables outside it. And of course, instead of this q, we had some further big complex formula. We would have to eliminate the existential quantifiers from the outside in, as we have always done. Now looking at the other side of the and symbol, and of course as computer scientists we are aware of the tree structure, and we know that this existential quantifier is at the top. It is not within the scope of y. Here we can get away with a Skolem constant, namely a. Now, if you have read certain other texts on Skolemization, or indeed very early versions of my own lecture notes, you will have seen treatments of Skolemization where your first step is to pull all the universal quantifiers to the very front of the formula. But generally, that gives you much longer proofs. When I say much, I mean an increase in length, which is very difficult to imagine using, let's say, ordinary arithmetic operators such as exponentiation. Yes, that much bigger. It's better to push quantifiers in. Now, it depends on the wording of an exam question, if we're thinking about exams, whether you are allowed to transform a formula and to what extent. But just to look at this example here, we have seen this formula before. If we negate this formula, okay, we're going to do a Tableau proof, so we want to negate it, and we're then going to put it on the left-hand side. So we negate it, see, for all exists. We convert to n and f, so I have px and not qy, being the negation of that implies over there. Now we could Skolemize this y immediately, and it would become f of x. But if we want, we can first say, well, this existential quantifier doesn't involve the first part of the conjunction, and maybe we should push this existential quantifier inside the conjunction. And then, having done that, we can pull it outside the scope of the universal quantifier. So we've pushed in, we've minimized the scopes of both quantifiers. And now, this existential quantifier is being outside the scope of for all x, becomes simply a Skolem constant. And if you tried to do a Tableau proof starting with this on the left-hand side, you know it would be trivial, because you would first you get rid of this and, then you would get rid of the for all, and then immediately you would get a contradiction between this p and that p. Well, let's do exactly the same formula, but this time I'm not going to do that last step. That is, I am not going to minimize the scope of the quantifiers. So because of that, when I Skolemize it, I instead get p of f of x, as I mentioned a moment ago. So with this, shall we say, uglier and more difficult Skolemization, we will have to work harder. The only thing we can do is for all on the left, and we do that. Now, as I have mentioned, when you do for all on the left, you do have the right to keep the universal formula. You might need it again, and in fact here, you do need it again. Because if you try and get a basic sequent, okay, here our next step is and on the left, and that makes sense. And now you might be tempted to unify p of y with with a p of f of y here and get a basic sequent, but you can't do that because of the occurs check. Now, in case you're confused by remarks I made about the scopes of variables in clauses in resolution, you might ask, what is the scope of y here? And I'm afraid the scope of y is the entire sequent. So these are definitely the same y, and the occurs check is indeed correct. That is to say, we cannot unify those two. There is no contradiction between py and not p of f of y. Well, what can we do? Well, luckily, I didn't throw this quantified formula away, and we can use it again. So we plug in a new variable for it, here at z. I mean, obviously the variable name is arbitrary, and in fact, the reason I chose it different from y, it is not necessary from a soundness point of view, but if I used y again, you can see that we wouldn't have introduced anything new and we would have been wasting our time. So we chose a fresh variable, and this time I threw away the quantifier simply because I knew it would no longer be needed. So finally we do this and on the left, and now we have, you can see in fact we can do a basic sequent in two different ways. So we have py and not pfz. We also have pz and not pfy. So either of those could be done. So the choice of y going to f of z is an arbitrary choice. And note that in this case, unification is inventing the term we need. In the past, whenever we did a sequent calculus proof, we had to eyeball the sequent and look at what terms were forming elsewhere in the proof, and then conjure up for ourselves the correct term. Here, unification is doing it. Now, a small remark, because I occasionally see students who saw this proof and somehow got the impression that in any sequent proof you are able to change any variable into anything else. So let me remind you, here we are doing a free variable Tableau proof, and in this context it makes sense, but this is the only context in which it makes sense. So don't take a sequent proof, write a sequent proof of a formula that is not even a theorem by somehow turning one variable in another, because that is simply cheating. Now, I mentioned already that when you use unification to replace a variable, you need to apply it consistently throughout the proof. And I have an example here showing you why that is necessary. You see, what we are trying to prove on this slide is not a theorem. This is equivalent to saying, okay, every number is even or odd, therefore every number is even or every number is odd. We know that's a fallacy, so this formula here cannot be a theorem. Obviously, we want to be sure that our Tableau calculus is not going to call it a theorem, so let's see what happens here. Now, the usual thing, as I keep saying, when you negate an implication, you take this thing positively, the left side positively, the right side negatively. And once again, inexplicitly, I have reversed the order. I don't know why. So I negate the thing that's on the right side. I push in the negation symbols, and for some reason I've put it here in front. But whatever. So this first part of our negated version is the negated right side of the implication. The rest of it is the original for all formula. Finally, I skolemize, and as I skolemize, again, this is kind of misleading. Strictly speaking, skolemization does not throw away the conjunctions, but whatever. So here we are then. This first existential quantifier was replaced by the Skolem constant A. The second one by the Skolem constant b. And we have as our original assumption there for all x, px, or qx, and we now try to get a contradiction from this sequent. So there's our sequent. There's only one thing we can do, which is to get rid of the quantifier. It's replaced by a variable. Now we have a disjunction. So in the next step, we do or on the left. We have py in this sequent and qy in that sequent. Here, we can unify y with a, and then the left side is proved. The left side is now a basic sequent. The problem is, now y is equal to a. So over here, it is not possible to replace y by b. Y can only be one thing. Now you might say, I shouldn't have thrown this quantified formula away. And indeed, I could have kept it here. Now, I'm not going to try and show you that if you keep doing this, so we kept the quantified formula here and kept spawning off more and more copies, you might think that that would be our salvation. In fact, it won't be, and the reason is because still the only negative occurrences of P and Q we have are not PA, not QB. And every time you spawn off another copy of the quantified formula, you're going to get the same phenomenon, namely some variable P, let's say Z this time, or Q of Z, and you're going to have to do both cases. So it is always going to fail, which is a lucky thing for us. So what I'm trying to show you, just to repeat myself, is how the mechanism of unification and the need to consistently instantiate variables in unification gives us sound reasoning. As a general rule, if you want to understand a formal calculus, look at how it handles quantifier proofs such as these. So just to remind you where we are, we have seen two separate calculi today. The first order tableau without unification, and that is just the sequent calculus with negation normal form and with only the left side of a sequent present. We've also seen a first order tableau with unification. There are many other things. There's also a lot of other terminology. These are sometimes called analytic tableau, for example, or semantic tableau. They're all basically the same thing. Now, a connection tableau is a very different thing. It's strongly related to the model elimination calculus we have seen already, and it is created from a particular problem having been generated, translated into clause form. Now, one of the cool things about a Tableau calculi is that they give you compact implementations. I mentioned that a very early piece of work by Wang produced an automatic theorem prover for first order logic, running on an IBM 504, if I'm not mistaken, and giving, for its time, very impressive results. Now I want to show you something else. I'm afraid I can't call this new anymore. It emerged, 25 or more years ago, but it is still an impressive thing. So this is a free variable Tableau theorem prover written as 5 prologue clauses. Now, you don't know a lot of prologue yet, and I'm not sure how much it's worth trying to go through this, but I will do my best. You have got, firstly, so this is a prologue predicate, this prove predicate, which of course is recursive, and what it is trying to do is work its way through, if you like, the left side of a sequent of a free variable Tableau. Now, in Prolog, and don't ask me why, A comma B means A and B. And just as A semicolon B means A or B. And as for this is going to represent a universally quantified formula. So going back to the top, this says, if I'm trying to prove or get a contradiction from a particular sequent, we look at the designated formula of that sequence, or if you like, the left hand, the first formula, simply syntactically. If it is a conjunction, what we do is we, as you know, we would normally split up a conjunction. That's how and on the left works. What we're doing here is very slightly different. We take the first half of the conjunction, A, and we make that the first argument in our recursive call. We take the second formula and we add it. So this ugly looking thing is simply to insert into a list. So here we have the list of unexpanded formulas. We insert B in front of this list of unexpanded formulas. So the formula in front is the one getting expanded here. A and B is getting expanded. Now in the next step, A will be expanded while B will be put on the list of unexpanded formulas, and its turn will come later. Incidentally, the third argument is a list of literals, that is atomic formulas and their negations. And they are going to be built up. What happens with OR? So A or B, as you know, with OR on the left, you have to make two proofs, and indeed here we have two proofs. What are the two proofs? Well, we have to do one proof in the case that A is true, another in the case that B is true. So if A is true, A needs to be further expanded. Now this one does not add anything to this list of unexpanded formulas. And the other parameters, that is the set of literals, this I believe is a set of free variables, and this is a counter. They are all passed down recursively. Now this, here we have a formula of the form for all, X is the bound variable, and FML is the body of the universal formula. And I have to say, a certain amount of black magic is taking place here, which maybe I shouldn't really get into in detail. The effect here is to check that the number of free variables does not exceed our varlim, which is our limit of the number of free variables allowed. So this gives us a way of controlling the search. If you set varlim to 1, for example, then you're only allowed to have one free variable in the proof, and that of course makes it incomplete. But you can, by increasing the counter, keep trying again with bigger and bigger variable limits. Now there's a crucial step here where, yes, what are we doing? Something very clever. We make a copy of the formula in some magical way. The original formula is put, yes, we are taking our list of unexpanded formulas, putting the universal formula. As I mentioned, you are allowed to keep your universal formula and expand it again, but it's being put at the end of the list so that it won't be expanded for a long time. What you wouldn't want to do is just keep repeatedly expanding the same quantified formula again and again and again. Clearly that wouldn't get anywhere. Finally, you take your new copied formula. I'm afraid this says FML numeral 1, by the way. I'm awfully sorry about that, but whatever. So this is an instance of the quantified, of the body of the quantified formula with a fresh variable plugged in. That is a new list of unexpanded formulas with the quantified one stuck at the end of it. And you'll see here we have the new variable that has just been generated is inserted into the list of free variables. And away we go. Now what are we doing here? This is where we have exhausted the other cases. So the formula to be expanded isn't an AND, isn't an OR, isn't a for all. So the only other possibility, it must be a literal. That is, it's either an atomic formula or its negation. A little bit of super ugly code here gives us the original negation. Yes, what it is the negation of. Right, this is a horrible way of negating this literal. Now, having negated the literal, we are now checking whether it is equal to the first literal in the list of literals. Or if not, you see the next step is to try it with the next literal down and so on. Sorry, this was a horrible one. Having failed all that, the final last thing to do, oh, and by the way, notice the call to unify here. This will be a proper unification that knows about the occurs check. The last step, if a basic sequent could not be done, so this was a basic sequent, this step, if that could not be done, then all you can do is shove your literal there into your list of literals, and you take the next thing out of the list of unexpanded formulas and you put it there and you try and prove using that. And incidentally, if in this case this list here is empty, then one cannot continue. Now the beauty of Prolog is that if there's a case that isn't covered, that is implicitly a failure. So we don't even need to include code that says if you run out of formulas to expand, then backtrack, because backtracking will happen anyway. Now please don't worry if this code doesn't make any sense to you. You haven't had Prolog yet, and even if you had, this is a pretty horrible hack. At least some people have said so. Nevertheless, it works. Now, how good is it? The problem with logic is that the difficulty of a proof can vary over such an immense range. So this prover is, I think, much, much more powerful than Wang's. Certainly much more powerful than any naive sequent calculus prover that you could throw together yourself. And by the way, this gives me a moment to mention that my own little sequent calculus prover is available on the course website. It's written in standard ML, which is of course the right ML. And if you want to play with it, you should feel free to download it and run it. This prover here is probably better, but none of these is remotely as good as a well-crafted resolution prover or SMT solver. And that is it for logic and proof. Thank you for bearing with me for all this time.